So welcome everyone to this first ever US-based LHON symposium. I've been dreaming of this type of gathering for over 4 years now, and it's truly exciting that it's finally a reality. I want to begin by thanking everyone who's made this dream become a reality, beginning with the UMDF, who have been incredibly supportive of everything I've asked in terms of creating an LHON project within their organization. As most of you know, LHON is a mitochondrial disorder like many others. Because our symptoms are usually limited to vision loss, we don't tend to have the same patient support needs as the other mito disorders, such as MELAS, LAYS, and others. Yet from a scientific standpoint, the work being done to find a treatment or cure for LHON and the other mito disorders is connected. So connecting the LHON community within the UMDF framework makes perfect sense. The UMDF was founded in 1996 with a mission to promote research and education for the diagnosis, treatment, and cure of mitochondrial disorders, and to provide support to affected individuals and families. Those of us whose families are affected by LHON have the very same mission, and collaborating brings the strength of the UMDF organization to the specific issues facing the LHON community. I'd also like to thank all of our presenters today who so graciously agreed to share their knowledge with us. Let me begin by introducing our first presenter. Fortunately for me, I live about an hour south of here, which means I'm relatively close to Los Angeles, where this speaker works. That means my family has the great good fortune to be able to easily visit one of the kindest, most intelligent, most caring people you could ever want to meet, who just happens to be one of the world leaders in the field of LHON. Having my LHON family under his care meant I could stop trying to be my son's doctor and could focus on everything else involved with supporting a family member affected by LHON. Let me read you his bio. Dr. Sadun began his studies of brain science at MIT and then earned a PhD and an MD from the Albert Einstein College of Medicine. His residency and chief residency were at the Massachusetts Eye Ear Infirmary, Harvard Medical. He completed a clinical fellowship in neuro-ophthalmology at Harvard Medical and then joined the full-time faculty at Harvard. In 1984, Dr. Sadun was recruited to join the full-time faculty of the Keck School of Medicine of USC. His research is centered on the clinical, psychophysical, and laboratory studies of diseases of the optic nerve and its connections with the brain. He was the first to identify several optic neuropathies due to systemic diseases such as AIDS and Alzheimer's. In 1993, he was selected and sponsored by the United Nations to lead an investigative team to determine the cause of an epidemic of optic neuropathy in Cuba. Currently, his research is centered on mitochondrial causes of optic neuropathy, such as LHON, and has developed a unifying theory of these diseases. In 1999, he received the Lighthouse International Pizarro Award, this organization's highest research prize given annually to one vision scientist or clinician deemed to have made the greatest international contribution against blindness. In 2012, Dr. Sadun received, as a combined prize from two organizations, AAO and NANOS, the William Wade Award, the highest honor in neuro-ophthalmology. Dr. Sadun is the author or co-editor of 4 books, over 270 peer-reviewed articles, and 70 book chapters. Please welcome Dr. Alfredo Sadun.
Wow, listen, I'm very embarrassed. That was very, very long and obviously very touching too, especially I love the first part. And so I'm going to see if I can find this on the internet so I can have my wife Deborah get a chance to hear it too. Thanks everybody here for being here. My thanks especially for the organizers of the UMDF, Dan and Kara, but most especially for Lisa, who has put together something that is unprecedented. I look around here and I realize that I have a lot of friends in the audience because many of you have come to see me as patients. And so there will be the risk that you're going to get to hear the same sort of spiel again that I've given in my office. But I think that what will make this particularly worthwhile is that there's so many of us in this room with different takes and different questions and different concerns that since it's a new thing, we haven't done this before, Liz, so we can define it as we go along. I would strongly urge that we make this an interactive session. And I would be perfectly delighted to stop at any point that somebody raises their hand. If you can't speak loudly enough, I promise Liz, I'll repeat the question so that it gets captured by the microphone. And we should certainly feel that this is a talk that is more of a takeoff from which we can discuss anything regarding what the title is, the clinical profile, which simply means what does it look like medically in the cases of Leber's hereditary optic neuropathy. So we have a deal on that?
Yeah.
All right. Now, you always have to have disclosure slides, and I'd like to point out that the research monies that we've received from Edison, none of them has been I was going to actually throw in Valerio since he forgot his disclosure slide, and myself. We actually make a point to not even accept a free lunch. It's wonderful to have this sort of sponsorship in terms of helping us with our research, but we don't take it as any sort of personal income, so that we have, in fact, an ability to turn to whatever is the best next solution. So how does it look when we have a patient with labors show up? And before I forget, I'm going to be using some of the laser pointer. And for this, thank you, Doug. As always, you've got my back. The typical situation I see in the U.S. would be like this. A young man, perhaps he's about 20. He's gone off to college. He was healthy, happy, has no knowledge of any family history of any disease. And so this is completely, if you asked him what his labors, he would have no idea. He may join a fraternity, and with the fraternity comes a fraternity lifestyle with a little bit more smoking and drinking than usual. And then maybe a month or two after that, he ends up losing vision in one eye. Now, we use the term subacute. Acute means you lose vision overnight. Chronic means month by month. Subacute means in about a week, the vision loss becomes significant. And at that point, you go off to the college infirmary. They send you off to a GP who says, I don't know what's going on, send you off to an ophthalmologist who looks in and says, I don't see anything. And there's an old adage in ophthalmology that says, when the patient sees nothing and you look in and you see nothing, it's optic neuritis. So they conclude it's optic neuritis. And optic neuritis is a common disease associated with MS. And I would say good 80% of my patients with labors are first told they had optic neuritis. And that's a little depressing because then they're told they probably have MS, and they end up with the tests for MS that all come back negative. About the time that everybody's scratching their head saying, if it's not MS, what is it? The other eye goes. And the prediction that had been made, because in optic neuritis it gets better after 6 to 8 weeks, doesn't hold true. Doesn't get better, the other eye goes. At that point, they decide to send the patient to a neuro-ophthalmologist, of which there's very few of us. Depending upon how you define it, there's anywhere between 200 and 500 of us in the world. And so it's hard to find sometimes. At that point, usually the diagnosis is obvious enough. It comes about from a combination of what we see in the exam and the family history. But there is, of course, a blood test. The blood test can identify a genetic mutation, which by itself is not the definition of the disease, but is very, very helpful. Now, having said that this is the typical presentation here in the U.S., I'm going to tell you that the presentation is a little bit different in Brazil. And we'll talk a little bit about the opportunity of having seen several hundred people with the mutation in Brazil. And at a certain point, I want somebody here to figure out what's going on in Brazil that makes for the different presentation. And then you jump up and tell me, and I don't know if we have any candy to give out or some other reward. But now, I have to admit there's two things that I find particularly compelling about this disease. One is that it strikes people down at the prime of their life in an extremely injurious way, and of course it tugs at our heartstrings, and I speak to you as the people for whom I'm feeling this. But there's also this extraordinary set of intellectual challenges where you have to scratch your head and say, that's just too bizarre, there's something really interesting here. And these are the four biggest intellectual challenges, for me at least, that really hooked me into wanting to spend more time from an intellectual point of view with this disease. So I'll give them simple names, but each requires a little more explanation. One, the problem of variable penetrance. You've heard that term, and it means this, that if mom has the genes, every one of her children will inherit the same mitochondrial defect. They're all the same. But maybe some will go blind and others won't. Typically, that's the case. So why should somebody who has the gene go blind and the next one not go blind? That's variable penetrance. From a genetic point of view, that doesn't make a lot of sense. Two, the problem of gender bias, which is to say that if you are a woman, you're not immune from the disease, but your likelihood of going blind with this mutation is much less than if you're a man. Now, it varies a little on the mutation type, this and that. But overall, I like to put things in a positive spin, but always say the truth. So when I have a woman who I find is a carrier of this disease, carrying the gene, I say, the good news is that being a woman, you're much less likely to go blind. When I see a young man with the disease, I say, the good news is you can't pass it on to your child. So there's a silver lining to each one. But there is a difference there in terms of likelihood that's gender-based. The third, which is really from a biological point of view amazing, is this problem of tissue specificity, which is to say every cell in your body, except your red blood cells, carries this particular genetic mutation. You might expect every cell in your body to suffer and cause a problem. But in labors, you never have a problem with your big toe. You never have a problem with your liver. So all these other cells don't seem to really care. The cell that cares the most seems to be the cell that connects the eye to the brain, that helps form this connection that we call the optic nerve, which is fundamentally a cable connection. And you've all heard the analogy I like. The eye is the video camera, the brain is the TV set, and they're connected by this cable called the optic nerve. The cell begins in the eye, extends back towards the brain, and that's the guy that gets damaged that causes all the vision problems. Why that cell of the thousands of different cells that the body has? And the fourth issue is that of catastrophic loss. Almost every disease, including mitochondria, that causes degeneration, that causes a problem, gets you bit by bit, nibbles at you. So Alzheimer's doesn't occur on the second Wednesday of the month. It's something that's slowly developed over many years, Parkinson's, etc. Whereas in this disease, it's at least subacute, which means that the vast majority of cells decided to quit in the same week. Isn't that extraordinary? Especially because these cells are not connected in an obvious way. So those are the four questions that keep me up at night. And I'm going to make a very arrogant statement that at least two of those four questions we got some good answers to. Questions number 2 and question number 3 we think we understand. But I have to admit the questions number 4 and 1 still keep me up at night. So it's too much to talk too much about mitochondria. This was the simplest slide that I had on mitochondria, and even that I don't want to dwell on. But you guys all get the idea that living within each cell are these little structures. We always describe them as little bean-shaped structures, although they don't always do that. They often fuse together to form long reticuli. But each one of these little bean-shaped structures has within them little components of genes, and that's the important part to remember here. These genes are separate from the other genes. So the vast majority of your genes line up on 23 chromosomes that you got from your father, 23 that you got from your mother, and that carries almost all the genetic information you inherit in a way that's pretty complicated, because whether the father or the mother dominate in terms of how they send the trait on is complicated. But this one's really simple, because there's a little speck of DNA, of which 13 particular genes are at play here, only 13 against 35,000 maybe for the nucleus. This little speck of DNA always comes from the mother. The father doesn't contribute. In this case, certainly, the father doesn't count. Just about the mother, and she sends this gene to all of her children, and every child from this point of view is an identical twin, or almost the case. So even though the other genes sort, and I told you a complicated way here, they're all the same. And the two big effects that we're going to talk about is that the mitochondria are supposed to make energy, that's the ATP part, and the byproduct of doing that is the reactive oxygen species, or ROS. And we think that these are the two major things that occur in change in the way they occur with labors, and that they have something to do with it. Again, the really simple version, we'll talk a little more about this, is that you've got a cascade of molecules that bring the electron around, and they do several things. By doing this and finally donating the electron to oxygen, they allow you to make this energy, they allow you to make the ATP, and they also generate this reactive oxygen species, which we sort of think sometimes are just bad players. They're sort of poisons that cause a lot of problems, but they're also used by the cell in a very useful way. So it's simplistic to say they're always bad. This is the picture that Doug was referring to when we were chatting before, one of my favorites, because it symbolizes an adventure we had in 2001 when we got to go to Brazil, a remote corner there of Brazil. And on this particular day, we needed to get the bloods of some 94-year-old man who lived at the top of they called it a mountain, but it's just a tall hill. It was rainy, muddy, there was no road. They couldn't come down to the clinic, so we decided to send the most expendable member of the team, me, up to get it. And so I'm wearing the raincoat. I'm on this rain-slick path. The Jeep couldn't go any further because it couldn't go across the log bridge to go up there. We still got a mile or so to go up the hill to get to the place. I brought along this box with a portable camera called a Kawa camera. The important part of that is that I knew I was going to slip and slide, so I volunteered to carry that as a sled when that would happen, and it did. And we did trips every year thereafter. By the second or third time, we had compiled a team that between the international group that would come from places like Italy and the U.S. and the locals that would come from various parts of Brazil, numbered up to 45 people on the team. So this was the field investigation team that every year went to examine this family. And I'm not going to get into all the particular major objectives of each year, but we did a lot of things, and we did it with regularity. And this is a picture to show you some of the local volunteers of the team. Every year, they not only gave of themselves for a week, taking all this time to work, I would say at least 16 and probably closer to 18-hour days every day for a week, to do so with very, very little compensation, except, the only compensation was food and these T-shirts, which, thank you, Fred. Fred paid for every year. My wife would design, and every year she would be trying to think of a prettier color. And so after a while, of course, they would not bring anything but the old T-shirts. So every day they would wear different colored T-shirts in bizarre combinations, except for the first day where I would hand out the new T-shirts when everybody would be color coordinated. Well, it all started with what we call index cases, right? The first case that we find the family with. In this particular case, it's a remarkable story because it's a woman who was in her 40s who lived in this relatively remote area, but had known that there was something going on in her family, that certain people were going blind. And furthermore, she had heard about the internet, and so she went to the big city, and when we would go around, by the way, and people would be introducing us to others in Portuguese, we had translators all around, they say, they're from very, very far away. These are visitors from a foreign land. The patients invariably say, oh, are they from Victoria? Which is the big city about 60 miles away. That gives you a sense of cultural isolation. So she went to Victoria, and there she learned to use the internet, and she did a lot of research, and she decided that what was going on in her family was LHON. And then further, she used that to find what we just heard about from Lissa, Fred Deal's organization, International Foundation of Optic Nerve Disease, iFund. And through that, she was put in touch with me. And this very poorly written letter, because she wrote it in Portuguese and had somebody else translate it to English, basically said, we got a whole family with this disease. My son's already lost vision one eye. I can reason, based on the fact that my two brothers went blind from this, that after one eye will go the other. It seems to me that this is the best time to intervene. My literature search of the world's literature doesn't show a treatment, but if there's a treatment that you guys have worked out in the last few months, I need to know it now. And maybe you'd like to come and visit. She was a smart lady. Because we got hundreds of people here. I think she said 100 people here. And imagine how much you can learn by coming to investigate us. Come visit us now. Which is exactly what I plan to do. So I call my good friend Valerio from Italy, and I say, let's go to Brazil. And he's all for it. We're all gun-ho, but cooler heads prevailed. And my chairman says, you're going to go down there. You're going to spend tens of thousands of dollars and discover that it's just a family of presbyopia. Presbyopia is reading glasses that everybody gets sooner or later. So his plan was a better one. We went with his plan, which is we wired a little bit of money to them. She and her two brothers and son used that to take a series of buses to Sao Paulo. A couple days later, they show up there, where my chairman had already organized. The chairman there would examine the patients, take photographs, and send us the bloods, all of which we did. And, of course, she was right. It was a 11778 mutation labors throughout the family. And she had gone there with her 14-year-old son who had lost vision in one eye, and you know the story. By the time he showed up, his other eye was involved. This is what the clinicians, the ophthalmologists would like to see, which is the pictures of the mother, which showed her nerves looked really pretty good, and her vision was about 20/20, although not perfect, and that's a story in itself. And this is the son, whose one nerve looks pretty good because it's so recent, and it takes a good 6 or 7 weeks for the nerve, once injured, to show that it's injured. The other nerve, you can already see it's looking pale. This is less pink than the upper picture. But the vision in both eyes had already gotten to 2200 in the recent eye, 2800 in the other eye, and it's going to keep getting a lot worse than that. And this is one example of one of the uncles of this young man who now the nerves are really pale. You see how white they are because those are pretty much dead optic nerves. And in fact, the visions of this particular person can either be expressed in the decimal system, which is what they use in Europe, as 1/100th of normal vision, or in the more traditional American systems, but really, really bad vision. Well, she was wrong, though, about one thing. It wasn't 100 members in the family. In the end, we counted 362. And in the end, we found 8 generations. The whole thing started with somebody who, in 1861, was born in Verona, Italy, and then at age 16 was given a ticket, imagine her courage, to go to Brazil, where they had found a husband for her, and she would marry and be the founder of this very extensive family. And the family lived in this rural area bounded by 3 cities. The big city was Victoria. It is a big city. And these 2 medium and really, really tiny city, this is 2 dirt roads that cross in the middle of the mountain that is that city. So they stayed in that little triangle, and that, for the purposes of an investigation, of course, turns out to be pretty useful. Now, this is how the pedigree, the family tree, looks like. Now, this is a group that's sophisticated. You've all seen family trees, but you've probably seen them just in a square way of being displayed. But when it's really big, this is probably the better way of doing it. And so there are 362 circles of squares all the way around there. The woman that I told you about, 1861, Maria Franchi, and by the way, most people had no idea about that. One of the unexpected beautiful things about this is this family every year getting together for a week with us, got to know each other really well, began to think of themselves as a family. And I think on the second year, they presented me with a little silver plate, and it brought tears to my eyes because it said, "From the family of Maria Franchi." They now understood that they all were defined by her. And she is this dot here and gives birth to the other 6 generations. So that's generation 2, though, because my colleague Valerio is not one to spend his time sunning himself on a beach. When he had August vacation, he, knowing that she was in this area near Verona, went after that and did a long time of searching church records and cemeteries until he could find her mother. And from there, working downward, found this branch of the family that still lives scattered mostly in northern Italy. So these 30 and these 332 represent the entire family. I'm going to talk about one little case, by the way, in a bit, and that's this guy over here. When we first started drawing out the pedigree, it was on a piece of paper, and then things got out of hand. I believe it was 12 pieces of paper taped together eventually, and then this is a picture that shows that, as well as what we looked like 13 years ago. I didn't have any hair back then either, but it looked younger. And Valeria, your hair was grayish. So just a few terms as we go forward about this typical clinical presentation. I think you know them, but I want to be clear. A carrier is somebody who's got the mutation. So if the mother's a carrier, all 100 of her kids are carriers, male or female, because she will always pass it on to her children. Every child is therefore going to be a carrier. It's even so simple that I can follow the genetics on that story. But if you lose vision, then you become an affected patient. So some carriers become affected. In fact, for this particular family, the 11778 family, if you're a carrier, there was a 50% chance you were going to lose your vision if you're a man. There was only a 12% chance of losing your vision if you're a woman. So this, depending upon the mutation in different families, but it's typically about 4 to 1, more likely for the men to lose vision than the women. The process of going from carrier to affected, we use the term conversion. That's why I said it takes place over a couple of weeks. It's subacute, a week or so. And the person converts from either no vision symptoms or really slight ones that the patient doesn't notice to serious vision loss. One thing that maybe Valeria will touch on is it also turns out that these numbers are the whole population. But the mother, who's always a carrier in this family, if she's also lost vision and is affected, these odds change enormously. Then I believe that it's 100% of the men, 100% of the sons are going to have lost vision in this particular family. It's not to say every family, but the odds are made worse for the son. And the odds are made worse for the women because if the mother was unaffected, it was 0% of the women. So that this represents the averaging amongst some women who are affected and some women who are not. Now, that made us think that there must have been other genes that the mother was contributing that had a lot to do with it, and it didn't turn out to be so simple. So in the investigations, when we had a chance, the patients came down to a clinic centrally, but this was actually the end of that journey I just showed you when I was going up that clay hill where we used that portable camera. Took a picture. This was a woman who was in her 90s and who still had pretty good vision. She was a carrier even at that stage. She's obviously had a full life, but a relatively unsophisticated one because every time this flash went off, and that's why she's grimacing because this isn't the first time she's trying, she would scream and run back. Having never seen electrical light before. Now, one of the things, and this is obviously a little sad, but also extremely important, is that most of this family also signed consents and said that we could go ahead and obtain the optic nerves and eyes when they died. She did also. So she represents, as far as I know, the only case there is of a carrier's eye and optic nerve. There are several cases of patients who've gone blind from that, who are seen but carriers obviously don't get medical care, or usually don't, and don't sign consents and have their eyes available. And we learned a great deal by looking at that because it was not normal. It wasn't very abnormal, but it was abnormal. Some of the typical characteristics came out in our family. The average age, if you threw everything together, was 29, but then it turned out that it was closer to 20 if it was the males, and in the late 30s if it was the females. And then we were able to have big enough numbers because the family was so big that we discovered that for the women it wasn't so simple. There were two clusters. One was in the 20s and one was around age 50, which we may or may not talk about today because I don't want to get to the end of my talk. I want to get interrupted long before that. But if we do get towards the end of the talk, we will mention the fact that menopause is probably a separate risk period for women, that estrogen is in some way a mitigating factor that helps protect against the vision loss. The typical patient had the same visions as we saw in that uncle that I showed you, 0.01, 1/100th of normal. So it's a profound visual loss. Now, it varies a little bit from family to family, but certainly we don't want to pretend that this is mild vision loss. And there were some patients who could only tell light and dark, light perception. And the best patient we had was 2400, which is well into legal blindness. This is, I think, an interesting chart because it shows you that, and at this point, the last word in the field, so we did change the textbooks in a few places. The last word in the field was that smoking and drinking did not matter. That was done on the basis of lots and lots of little case reports that are then collected and what they call meta-analysis. But the trouble with meta-analysis is you never knew the patients, and so you don't know exactly how it was done. But while the meta-analysis said it didn't matter, for our group at least, it really didn't matter. Now, if I had to do this chart again, I would have done it differently because I want you to read it from right to left. So toxic exposure turns out to be almost exclusively pesticides. This is a very agricultural community. And the controls represent people who are not part of the family genetically, just going in with the family members. And so this is a very agricultural community. 16% of everybody there was exposed to pesticides in high volume. But almost half the patients who had been blinded by labors were, so that clearly meant that this was a risk factor to cause that blindness. And what's interesting is if we looked at the carriers, the number is 10%, which is even less than controls. That's actually what you would expect, because some of these guys that were higher ended up in this column. So we have subtracted from this column individuals who lost their vision, and that is further evidence that pesticides were a trigger. The emphasis, and the reason I put this in dark yellow to dramatically point out, is the smoking and drinking really does make a difference. You know, we didn't go there just as this purpose, so we probably could have done a better job, but we basically didn't characterize the amount of smoking and drinking. We just said, if you smoked 10 cigarettes or more a day, you're a smoker. If you drank more than 2 drinks a day, you're a drinker. And the numbers in the population that were not genetically part of the family was 26% for the smokers. And then later on, I did have a chance to read the epidemiology in Brazil, and this number turned out to be 29% in Brazil. So it's pretty close to what it should have been. But the group who had lost vision, 2/3 were smokers. So clearly, again, a very strong risk factor. And once again, notice that the people who are carriers is smaller in number than the average in the population. 2 interpretations. The one I gave you before, that some of these guys who smoked weren't carriers anymore. Their smoking dragged them into this column, and they became affected. It's also possible that at least some people sort of got the feeling that, gee, I'm at risk, and I got to be super healthy, and they may have avoided smoking on purpose to drive this number down. Yes?
Does that then extend to all types of strategies, household cleanses, shampoo, body products, all those things?
The simple answer is we don't know. These things were not examined bit by bit, although we came close to answering some of those questions. We did produce these ridiculously gigantic spreadsheets, and a colleague of mine at UCLA, Stan Shine, did try to look at that, and so I can at least tell you we couldn't find it. So I do have some people who just assume that if it's bad for you, it must trigger labors. I don't think that's true. I think there's particular classes of things that are bad for you that will do that. Drinking, same thing. In the population in general in Brazil, about 1/3 of people drink at the high level that I was defining, but amongst our patients who had gone blind, it was 2/3. And this number here, again, is pretty close to that. In this particular situation, it's higher probably because this is a remote rural area. Yes? Yes, well, we had to, the question is how many drinks a day, and we defined 2 or more as our line. Now, that's why some of you have heard me say that taking 2 or more drinks a day is bad for you. That's not to say that 1 drink a day isn't, although I actually don't think it is. But we don't have a point-by-point scale here where we can say 4 is 3 times worse than 3 or something like that. We drew the line, and there's where we drew it. And if you, by the way, did both, smoking and drinking, the numbers are even more obvious that it causes a risk. We did lots of things that I'm not going to get into. Some very sophisticated tests. I've had people approach me a few years after this saying, I want to come and get all these tests done and visit you in Los Angeles where I see my patients in the U.S. And I say, well, I can't. I don't have all those tests. You're going to have to come to Brazil to get it all done. It's the only place in the world that all these things can be done. Because one of the rules that we made, because a lot of people wanted to join us in our investigations, was you could not come, because it would overwhelm the infrastructure of this tiny little place, unless you had something very special to offer. You had to have technology that you pretty much could say you were the world's expert in order to come. So we got people who invented techniques that now are more widespread in use, like multifocal ERG and multifocal VR, who came down to do it there. So these patients were getting a level of sophisticated tests that no one else on earth was getting with labors. So I want to give you just 3 take-home messages that we learned from all these studies. What did it teach us about patients who had lost vision, the affected, who had not lost vision, the carriers, and what was there about that process of going from carrier to affected that we could characterize? In terms of affected, we learned something that the textbooks... Oh, yes?
I want to ask a question about something you said before.
Sure.
Subacute.
Right.
You said a couple times it's 1 week.
Yeah, let's say 1 to 2 weeks, about that.
For me, it was 6 to 9 months of process.
Well, you bring up a good point. That would have fooled most people, including me, because it's almost never like that. But one of the rules about this disease is there are exceptions to every rule. You are exceptional, but that you probably already knew. That's chronic. That doesn't go along with labors, but it doesn't disprove it either. We have seen a few exceptions of every sort, and that's how I'd characterize it. You can give it a name too, but the point is that 99% of people would be shorter than that with labors, but there's that. There's also a few people who, once they lose the vision, get it back. It's not complete recovery, but at least a little bit of recovery. And that, too, is against the rule, but it happens. So a lot of other things do happen, and that's part of the mystery of this disease, that not only you have this variable penetrance, that is to say you can't predict who's going to lose vision, but the exact process of the losing vision, how much vision loss there is, how much recovery, that's impossible to predict, too. Okay, so the patients who had gone blind, the rule that was in the textbook was it all happens, as you just pointed out, usually subacutely, and then maybe a little bit more progress for the next few months, and then it levels out, and that's the way it's going to be forever. Well, there's 2 reasons that rule was made, and they both were wrong. One is that patients are tired of going back to their doctors if they have no further answers to give and offer no hope. So most patients stop coming after about 8 or 10 months. And so nobody knew what was going on with their patients after that. 2 is most ophthalmologists have a hammer that they think the whole world's a nail, the saying. That is visual acuity. That's the only measure they know about how to see how the eyes are doing. And I'm on tape here, right now, Alyssa? I'll go ahead and say it anyway. My adage is visual acuity is a very shitty measure in LHON. It just doesn't capture at all what's going on. So that's another reason they just didn't understand that, in fact, it keeps getting worse. The natural history of the disease, untreated, do nothing, is that year 2 is worse than year 1 and year 10 is worse than that. It just continues to progress. And in fact, we have a patient that was smuggled from Italy by Valeria to me who was, I think, 76 when she died, and she had lost her vision at age 25. And when we did the electron microscopy, you could see that there was some axons that had died 4 days earlier. Just that continuous a process. But it does so in that is predictable, the order of the fiber loss, and we'll talk about that. The second take-home point, the carriers, which we say asymptomatic, which means they think everything's just fine, no vision loss. They, in fact, sometimes have things going on in their eye. About 20 or 25% have a little bit of, not exactly swelling, but it looks a little bit like swelling of the optic nerve when you look in the eye. Up to 50% have color vision deficiencies that nobody would pick up. Not only the patient doesn't pick them up because they say, I see red, blue, and green, but the ophthalmologist's routine color tests don't pick it up either. So it takes specialized testing. And most amazing of all is this relatively new technology, OCT, which allows us to measure how many fibers there are in the eye, but unfortunately not exactly. It measures the combination of how many and how big. But 80% of the times that number goes up. Now, the machine was designed to measure loss. So the way they display it is that it doesn't care about things being too high because it figures, how can you get more fibers? And you can't. Fibers never grow in. But because it measures a combination of fiber number and fiber size, when the fibers swell, it looks super good on the test. And that's what I'm talking about. 80% of men have a super good set of fibers, yes.
Do these things in carriers predict it all?
That's the next slide. That is the next slide. So in women, it turns out that it's a much smaller number. I don't remember what it was, but it was like 20 or 25% had that swelling. So right away, that raises your question, which is, well, we know men are more likely to lose vision than women, and men have much more of this swelling if they're carriers. Could these things predict who would get? And that's the next part. This conversion can, in fact, be shown by these very tests. And so I thought I would give you an example of this with one particular case. It was the one I showed you way out there on the pedigree. 14-year-old young man. He wasn't particularly interested in participating in the study. He was perfectly fine and happy. His mom made him do it, and her second cousin made her do it. And that's the way these studies really work out well, when you got one dominating individual who says everybody's going to have to show up every time. And so they all had to come. And he would come in every year, and we'd examine everything. And initially, we didn't have enough confidence in ourselves. We actually wrote down probably normal, but we went back and we drew and took photographs of what on the second and third year we realized was not normal. He had the very things we talked about, these little swellings around the optic nerve head, funny little blood vessels associated with that. And in his particular case, even more. This is his nerve, and we won't dwell on it, but you may notice that instead of having sharp edges, especially down here below and over there, they're sort of fuzzy. And just beyond that, there's a couple of tiny little blotches of red. Those are funny blood vessels that we call telangiectasia. And that's very rare, and that does predict this. Yes, but less. Yes, sir. That's a great question, and I'll answer in about 3 slides.
So did this 14-year-old later go?
Now you're 2 slides ahead of me. Yes, sir.
Can you go back and explain more? You said that the fibers keep dying no matter how long
Yeah,
they keep dying.
that is true.
You said
If untreated. I think that with treatment that doesn't happen. We'll talk about that a little bit later. You guys, I promise to get to those very subjects. Yes, sir. No. As far as we know, nothing else is going on in any other organ anywhere else. And by the way, not every patient who loses vision has telangiectasia. About half of them do. And not every patient with telangiectasia loses vision, but it is a predictor.
Is that a difference between resilient population?
No. This is actually, Nicole Skalainen did a large population in Germany, and this is old news. It's clearly established that telangiectasia can occur early on before you lose vision. So I like to show this slide to ophthalmologists because they always ask me what's good to test with, and I like to say there are 3 particularly useful tests. One for structure, the OCT, that tells you if the nerve fiber layer is swollen early or whether it's the opposite, thinned later, and we'll talk about that process of going from one to the other. Color vision, somewhere between 50 and 60% will have subtle changes on them, and just looking, you can see 20 or 25% have these little changes that we just talked about. So those are the 3 things that I advise. If you want to check a carrier and have any sense that something bad's happening, those would be the 3 things to do. We covered that, but to your question specifically, we also discovered not only that there's swelling of these fibers, but it occurs in a very specific order. It begins on the temporal side, that's what the T stands for, then the inferior, then the superior, and lastly nasal. So not only we can anticipate what's going on, but we can anticipate what stage we're looking at it. If you've got a patient who's got nasal swelling, you're at the end of the disease process. They already lost vision. And this was the curve to answer your question. So this was a work by Barboni, who's part of our group, and he's at Bologna. And so he said, let's look not at the nerve fiber layer as a one-summated everything, but look at it by those quadrants, based on the fact that we had already seen that very phenomena on both the examination of the patients and on our pathology. So he characterized it as, and here's time at the bottom, and this is normal is 0. So everything above zero, the test would say is supernormal. We're wonderful, we're happy, but of course it's the opposite. It is swelling. And the first thing to swell is the temporal. The next thing to swell is the inferior. The next thing to swell is the superior, and then the very, very last thing to swell is the nasal. And when the nasal is swelling, the temporal's already gone. And now here's the biggest problem with the OCT retinal nerve fiber layer. It's wonderful, it's objective, it's quantitative, and it's very useful, but it's measuring two things summed. You remember an algebra problem that had two variables in one equation? You're in trouble because you couldn't tell how much of one, how much of the other. The fibers first swell and then die. And so if we had looked at the fibers on the nasal side, at this date here, they would have been perfectly normal because there would have been just enough swelling to offset just enough. So what you really need to do is this test over time to know which direction you're going and what's going on. Any given spot test, you're not sure what the combination adds up to. So this is to show again, begins temporally inferiorly, and it ends superior and nasally in this march. Well, that's the same march that we see on histopathology. We have a total now of 17 nerves from patients with Leber's who've gone blind, which is 17 of the 19 that exist in the world, so we have a pretty nice library of this. And I've chosen 4 to be good representations of what we're talking about. Each of this is a cross-section of the nerve. This is the patient who's died, who's donated their eyes and optic nerves to us. And each of these cross-sections is stained, a brown stain for where the fibers are. So this is the normal part of the fiber. This empty zone here that's white is where they're gone. And they've all been oriented the same way. They've all been oriented so the left is temporal. And so I've taken a case of mild, moderate, severe, and very severe vision loss. And there's that same march with temporal, inferotemporal, everything but nasal, and just tiny little corners super nasally left over. This is the march that we had seen when we do the examinations under the microscope. Now, without dwelling on it too much, we came up with the formula that would predict that, because these fibers are not all the same size. And we thought, you know what? The real problem, if it is these ROS, is the ROS are perhaps injurious to the system. It would seem to us that the stress, which I've represented by X, would be due to the amount of work that the cell has to do compared to how many mitochondria it has. And without going into too many details of this formula, it comes down to the end that 2 over R, where R is the radius of the fiber, is the reduction of all this, which tells you that the bigger the cell is, the less strain there is. And so then we went back and did something that hadn't been done in ophthalmology before. We measured these cells. They've been counted before but not measured. And this poor fellow named Billy Pan took a year off from medical school to hand measure 100,000 axons, just tracing them around. And when he did that, he ended up with numbers that I have more complicated pictures, but this is the simplest version of what he did, which he put into a 1 to 5 range. The smallest fibers are where it says 1. The next size where it says 2, 3, 4, 5. And you can see that's exactly the march that we talked about. So we pretty much confirmed the math model. The fit was exquisite, that these fibers, for sure, the smallest fibers are the first to be injured and the largest are the last. Okay, now, this is one of the sets of rules that answers one of those questions I asked you about tissue specificity. We know now that this is a disease that affects neurons. That's not so surprising. The statistics I like to give are this. 2% of your body weight is your brain. You know, we're really proud of our brains. It's just 2% of us. If you took my brain out and put it on a scale, it would weigh 2% of what I weigh. And yet 20% of the oxygen consumed by my body is consumed by my brain. It is a very expensive organ. It's a high-maintenance organ from the point of view of calories and oxygen. So why is that the case? And that's not so much that the neuron itself is doing all that work, but neurons talk to each other by these long extensions called axons. And every time that the neuron has a signal, it causes what's normally an electrical potential across that membrane to be discharged. And then at every point on that membrane, you've got these molecules that use up ATP to recharge it. So imagine a battery being discharged over and over again every single time one neuron talks to another along this long axon. Now, evolution is a very clever thing, and in addition to doing something that everybody talks about in our field, which is produce myelin, which is basically insulation, but insulation is not continuous on these axons. It works in these large segments with tiny gaps in between, and the only part you have to discharge to send the signal is at the gaps. We call that saltatory conduction. So it jumps from gap to gap, and the 99.9% of the axon that's myelinated doesn't do any work. Fantastically good for 2 reasons. One is it speeds up the conduction. Everybody talks about that. But also because it reduces the energy load on the brain. So now we can understand that in general rule, neurons are going to have a lot of work to do. Yesterday at the meeting, Janice asked the question, said, you know, the most metabolically active cell in the body isn't the neurons in the brain, it's the neurons in the retina. And we call those rods and cones. They are incredibly hard those are really high maintenance wives. They just consume an enormous amount of energy because they have to be constantly discharging. Whether they're signaling or not, they're always doing it, depolarizing. How come they don't get into trouble? And the answer that I shared with her, I could have been wrong, Janice, but was that, well, the numerator was really bad according to my equation, but the denominator was not so bad because they had a lot of mitochondria. They have a whole stack of them called the inner segment. But axons have a problem. They can't do that. They're long and skinny, and some of them are really small. They can't accommodate the extra mitochondria. And, of course, the longer the axon, the more the problem is, because you still make all your mitochondria in the cell body, but you've got much more energy to extend. If you don't have myelin, as I mentioned, that's a bigger problem yet. And so I forgot to give you the biggest punchline of all, which is that all active axons in the brain have myelin. There's a few axons that are pretty inactive. They're almost hardly ever fire, and they don't. But the active ones do, with one big exception. Our friend, the retinal ganglion cell in the eye that forms the optic nerve. And why doesn't it have myelin in the eye? Turns out the retina is sort of put in upside down. They call it the inverted arrangement. Light has to travel through the entire retina before it hits a rod or cone, which means it has to travel past these fibers I'm talking about. Myelin is opaque. So if you had myelin in the eye, you wouldn't see a thing because it'd all be in the shadow of the myelin. So evolution had to say, well, that's a trade-off we'll have to take, but no myelin in the eye. Therefore, a tremendously expensive process in the eye. And finally, as I showed you with the numbers, small axons are going to be most problematic. Yes, sir? Yes, we do see things. We see some bipolar dropout, and we see some problems with the outer segment, not the inner segment, but the outer segments are shorter. And I see Janice nodding here because she's done a lot of physiology experiments and knows that while they're in pretty good shape, they're not perfect. No, I don't recall anything being wrong with the RPE. It was the rod and cone outer segment that was unhappy. Yes?
You mentioned tissue specificity, but one thing I've been really struck with is how many of the patients I've talked to have gone through very serious depression. So has anything been done to look at brain MRIs and to evaluate whether or not there might be a psychiatric phenotype, especially related to, and I'm not just talking about brain, but losing vision.
Right. So the question is, many patients with labors suffer depression. Could this be an actual direct organic component of the disease? Well, I don't know is probably the simplest answer, but it's based on several points. One, I'm unaware of any MRI changes that characterize depression. Two, patients who've lost vision certainly have reasons to have reactive depression. They've had something that has altered their lives. Three, carriers are living under the fear as well as the grief of their sibling or cousin who's lost vision. So there's certainly many other explanations. That having been said, of course I gave you the simplest version. Labors is not totally tissue specific. There are other things. Some patients with labors do have peripheral neuropathy and this and that. So if it turned out that there was some sort of brain component of this, it would not surprise me. Yes?
My children have a secondary LHON mutation, and they have been dramatic responders developmentally to creatine. I found one peer-reviewed published article talking about low phosphocreatine levels in the brain, which is a big connection to all sorts of mental health issues. So I didn't have a about that.
Looks like he has an answer.
So if you measure things in the unaffected tissues like muscle or brain with sophisticated ways like MRI spectroscopy, you see phosphocreatine, you see that the metabolic setup of these tissues is not perfect. So you do have less phosphocreatine. And what we do in Bologna, we do a little bit of exercise on a pattern looking at the muscle from the labor station. So you actually deplete your phosphocreatine because you use that as an energetic molecule, and it takes longer for labor patients to recreate that phosphocreatine, which is an indirect indication that the respiratory are not producing symptoms.
So, sorry, go ahead.
So far what you've discussed, does it pretty much stay consistent with Loans Plus, or is that a whole?
No, it's not a whole thing. So one of the things I think that all of us know is that although we're talking about classical presentations, and my clinical profile I want to give the classical one here, these presentations have a lot of overlap from one mitochondrial disease to another. So it looks like it's always a relative tissue specificity, not an absolute one, and that an LHON plus would be an example of that. So I wanted to leave you with this impression that what is really going on in this disease is the smallest fibers. And what do the smallest fibers do? They provide you vision in the dead center. So what does a Leber's patient present with? Blindness in the center. We call that a scotoma. That's just Latin for darkness. So there's a central area of darkness. And then they have poor color vision because the small fibers are the ones responsible for red, green, and blue. So if the patient, in fact, maintains the size of the scotoma from extending too far out, they're doing well if it's smaller. And if they are small enough, they see a little bit of color around that. That's great. But if the patient has bad disease, the scotoma is very large, and they have no color vision at all. But in both cases, the visual acuity is bad because it starts centrally and moves out. So as I'm signaling with my hands, you can have a tiny central scotoma and terrible vision, but it's still a lot better than having a giant central scotoma. And visual acuity is not the best measure of that. So I'm not going to get too much into some of the science here, but what are we going to do about it? Well, maybe what we should be doing is trying to manage these reactive oxygen species, which we think are at least part of the culprits. We have chemicals that might be able to counter them. You can manage them, by the way, by not getting exposed to it, like smoke. You can take chemicals that might help with those, and you might be able to correct the genetic block in the first place that made them. Those would be the general strategies. So I want to leave you with about 3 or 4 slides in terms of our understandings. One, the environmental risk factors are certain, they're big, and there's something everybody should be maximizing what they want to do about it. So that means no smoking of anything, tobacco or non-tobacco. Don't have any smoke at all. We have a number of patients who lost vision while they were cooks, and probably standing over a burning steak isn't good for you either. I try to emphasize that steam is not smoke, and that's fine, but smoke is bad. One of the more dramatic stories that I've been involved in and published on was a woman probably about 34 who lost vision, and she lived near Sacramento. And then only a month or 2 after that, her 9-year-old daughter lost vision. We just said that women don't tend to, and that's pretty extraordinary that they both lost vision so quickly, one after the other. And then the 4-year-old daughter lost vision. And the answer turned out to be that they were living downwind of a tire fire. And some of you might know, tires burn a very dark, terrible black smoke filled with reactive oxygen species, and they can't put it out. So they just let it burn for months or even sometimes a couple years before it burns itself out. Meantime, her house was just in that column of smoke that was blowing across. Now, I made the mistake of talking with the EPA and telling them how interested I was in this, and they said, we will get you a chemical analysis of that smoke. And they sent somebody out to do it, and they sent me, back in those days, the printers had little holes on the side of the printer paper, and I got this reams of folded paper with hundreds and hundreds of chemicals I never heard of. So it's not so simple as to say it's that reactive oxygen species. It probably was an integral of all these weird things going on, but smoke is bad. So in terms of why it happens, I sort of mentioned it, and I'm going to jump over a couple of these slides to get to this one. Remember before I showed you this chain of events. It's actually not exactly chain because complex 1 and 2 sort of work in parallel. And then you can see that since you're passing the electron 3, 4, and 5, this would be a really bad place to block things because it blocks everything up. So in a way, this explains why Leber's is such a mild mutation, because by knocking out complex 1, the system still can drive and make through ATP. It's compatible with lots of things. So it's really a relatively minor, from big picture point of view, mutation, major enough if you lose vision. But when you block this electron, you do a couple things. One is you reduce the amount of ATP produced, but this electron has to go somewhere. That's where you generate these ROS that we've been talking about. And we have a few other diagrams to sort of, I'm going to go to this one, put the whole picture together. So imagine you've got this mitochondrial DNA mutation that blocks that electron. It's going to do 2 things. It's going to produce less ATP, or energy, but the part of the story I want to emphasize is going to produce more of the reactive oxygen species. Now, it turns out that the reactive oxygen species have a role, too. They're not just poison floating around. They are a signal, and part of that role is to signal the electrical potential of the mitochondria to become less. And that can open up little pores that allows for certain chemicals to come out that set off a whole cascade of events that actually tell the cell to commit suicide. Now, that's a very important signal. There are circumstances where cell suicide are absolutely critical and wonderful for the organism, but under the wrong circumstances of a false signal, they're going to lead to a disaster as the cell dies. Now, in the meantime, this is the cell that is the retinal ganglion cell that has to send its fiber up and around before it leaves the eye. And so in this area, it's unmyelinated. What I was showing with this diagram is back in the brain, it does have myelin in these little clumps, and all the work that's done in between, which is why I put the little footballs that are supposed to be mitochondria there. But up in the eye where it has no myelin, it's crammed full of these little footballs, and that's probably why the retinal nerve fiber layer on OCT first swells up, and then when it reaches a critical threshold, dies and shrinks down. And it does this in the march that begins from the smallest fibers on the infratemporal side and finally gets to the largest fibers on the supranasal side. So we should finish with a discussion of what we do about it. And I have advised that we should discuss some of the science, such as the different types of mutations and whether you have all your mitochondria bad or a mixture of good and bad, which, as everybody in this audience knows, we call heteroplasmy. I don't think that labors can be managed over a long distance, so I do encourage patients to go to see at least somebody who's seen a lot of these cases, and also to have parents and siblings attend for several reasons. And I strongly believe that education and understanding are an excellent way of dealing with it in terms of compensations and strategies, but also just to get some sort of ownership and control of the situation. We like to do a battery of tests, but emphasize, especially if people come from a distance, as many of you do, that come to see me with less regularity, but get from your ophthalmologist more locally OCT and visual fields, because this is the single best measure of the structure, how many fibers are left. And this is the best measure of the function, how big is that scotoma. We don't mind getting the visual acuity here or there, but that's not the important measure. And finally, what I tell, and as I have told, I hope everybody who has seen me in this audience, is these sort of 8 points. One, what are the genetics? What is the prognosis? How are things going to go? The genetic counseling that you're going to hear much more about is just to emphasize again that as a man, there's absolutely no risk of passing this along, that you have to avoid every form of smoke, including tire fires, that you should not have much alcohol, and we just drew a random line in the sand, but I don't know what much means in terms of whether one drink really is bad for you or not, but we do know that more than 2 drinks certainly is. Just common sense things in terms of maybe antioxidants and diet and vitamins, but I really don't have proof that any of those work. That there's a class of antibiotics that are meant to poison bacteria in exactly the same way as they would poison mitochondria, because mitochondria were once bacteria a billion years ago. So those antibiotics, not surprisingly, especially if taken chronically, will tip the balance in a very unfavorable way. There are a certain number of medications available, and idibinone is the one that most patients are put on. There's Epi-743 that some of you know about, and yes, go ahead. We actually have a printout that I would rather rely on that you can get on LHON.org. I have more confidence about some of these. The ones that I'm particularly concerned about are 2, ethambutol and linezolid, but I'm concerned enough about chloramphenicol and streptomycin and its cousins, gentamicin. So there's a few antibiotics that we will list in an order of likelihood. Probably more important than the order is the quantity of the antibiotic, and probably more important than the quantity is the duration of treatment. I'm not aware of anybody having gone blind from that 1-week treatment that is often given by the emergency room. And while we're here all together, I want to caution everybody about what I call the China scam. You can spend between $50,000 and $60,000. You can go to China, not to a nice big city, big university, or places where they know what they're doing, but some tiny little place in Western China where they will take your money and give you stem cells. They basically give the stem cells in a couple of different places, but what they take as stem cells is your own blood, and then re-inject it into these places and tell you you're getting stem cell treatment, which I guess technically might be true. Fortunately, I've actually looked at the numbers. They dilute it out so much that it probably doesn't do any harm. But there's no chance that it's going to be able to get a new retinal ganglion cell to grow in your eye, to grow out to the optic nerve, to grow down the optic nerve, and to synapse, make a connection in the right place of the brain. So there is absolutely no chance it's going to work in Leber's. I don't think there's any chance it would work in any of the optic nerve diseases. And the basis that they sell this is a bunch of testimonials on a disease called optic nerve hypoplasia. These are kids who are born with too few fibers. And it turns out that the brain is plastic. It knows how to adapt. So naturally, around the ages of 2, 3, and 4, the brain learns to maximize this underrepresentation of fibers and naturally gets better. So they have a whole bunch of these before and afters. 3-year-old kids who came in, got the therapy, and a year later started watching TV again. And that's just the natural history of the disease. It has nothing to do with the $60,000 that they took for it. And my general advice is when a great breakthrough occurs, I expect it'll occur at great universities, or at least be used by great universities. So when you hear about Harvard or Yale or University of Pennsylvania doing it, or the great universities of Western Europe or even China, pay attention. But if it's a place that no one's ever heard of, please be on the lookout. Well, I think that there's no question but the stem cell is a legitimate science. No question that stem cells can replace tissues. The hardest problem we're facing, but to answer your question, yes, it'll eventually happen, but not in the near future, is the problem that I will call specificity. If you're missing liver, getting new liver cells regenerated, it's fantastic, wonderful, and you're home free. But if you're missing some optic nerve fibers, you've got to not only get the new fiber in the retina, you've got to get it hooked up to all the right neighbors. And then it's like a piece of circuitry. It's got to now go up out of the eye into the brain, and not just anywhere in the brain. It's got to go to the exact part of the brain that matters and the right cell and the right dendrite. It's an unbelievable precision situation. So I would say right now it would be the equivalent to having that cable that connects your TV set and your video camera that I started with. Somebody just cut it with a hatchet, and somebody else says, I got some liquid solder, in other words, stem cells. I can pour it here, stick it together, and it'll work, right? Not unless you can line up every bit of these fibers in terms of the message would it matter. So yes, one day we'll figure out how the embryo did it in the first place, how it learned where to go in the brain, then we'll be there. That's not tomorrow. I think at this point I'm going to turn it over first to you, because we want to have a few more minutes of discussion, and then to Valerio. Thank you very much. It's been a real privilege to speak with you. Did I get enough questions along the way? No. Good. I got some more coming. Please. No. One of the problems with getting idebenone over the internet is that there's no FDA control. Now, the good news is that Santera, which makes idebenone for use in Europe, England, and so on, has on a few occasions spot-checked the idebenone available over the internet with the thought that maybe it's going to turn out to be talcum powder or something like that. And the good news is when they did that, they complained bitterly that this brand was 5% too strong, this one was 7% too strong. And since we don't have an exact dosage anyway, as far as I'm concerned, that's validating that the stuff that they've tested actually is idebenone. But to compare one brand to the other, that's what the FDA would normally do, and this is not FDA approved, so you're on your own. The most I can tell you, though, is this. We've had a few cases that we think were really particularly excellent responders. Patients who had not done well, started idebenone, did brilliantly well. And so we've used those brands, again, circulating around saying we think maybe this is good stuff. But the answer is no, I don't know.
The problem with the idebenone being sold by the websites is not that there is no idebenone there. The molecule is there, as Alfredo was saying, but it's a matter of how pure the compound is. And FDA and the agencies require a certain level of purity, which is not obeyed by these brands.
But so far, yeah, Santero is on the lookout to show one day, oh, look, it's just talcum powder. It's never found that. So there seems to be some level of legitimacy to them. Yes?
I'm so like to understand, so the fibers keep dying over a lifetime. So I've been affected for 15 years, and they will continue to die unless treated. I missed the part about the treatment aspect.
Well, that's actually the next lecture. The title of the next lecture is Treatment Strategies.
Yeah, we're eager.
All right, good. I set you up, Valerio. Yes. There's no question that there is such a thing as LHON+. There's no question that, as we said before, that there's some cells that are more vulnerable. That doesn't say that all the other cells aren't. And neurons in general are vulnerable. So, yes, you could have other elements involved, but I don't think any of us can really say, in this patient, this symptom of whether it be depression, as was brought up before, or bad sleep, all these things potentially could, but we don't know if they are connected. Only very, very late in the game for patients who are untreated. So one of the things that we notice is that even though some of our patients have bad visual acuities, they come and go on their own. Whereas the patients who we used to see, who don't have any treatments, came and went with dogs and canes. There's a huge difference in terms of keeping your peripheral vision, in terms of being able to get around, especially semi-familiar environments like your own home. So everybody here in the audience knows what I'm talking about. The visual acuity isn't a good measure not only of the disease, but of how well you can function. And that peripheral vision can be extremely useful to you. And it's maintained and treated. That's extremely unusual. Well, one of the things that can happen, of course, is you can have more than one disease. So in addition to what we talked about before, which is there are anomalous versions, there's even a little overlap, for example, with MS and optic neuritis. And while I said, as is the case, the vast majority of patients who are diagnosed who have Leber's are diagnosed mistakenly with optic neuritis, there's also a few patients who have both. And some other diseases, just to give two examples, glaucoma and often optic neuritis can have peripheral visual field loss too. I just don't know. Right. So in this room are probably two of the world's greatest experts on the issue of what you're calling secondary mutations and whether they are in fact aggravating the condition or perhaps rescuing certain conditions. There may be some selection pressure for evolution to actually give you certain combinations. I'm not going to answer the question in their presence because they have a better answer than I do. Yeah. You want to address that now or wait till you get up? Okay. Well, we actually just heard a lecture on that, and the answer is, in many mitochondrial diseases, very much so. To my knowledge, no person with Leber's, this being such a mild version, has had trouble. But it is in the nature of anesthetics to add to the burden of the mitochondria. So while I think that most Leber's patients will do okay, it's certainly something that should be mentioned to the anesthesiologist so that he may choose to have a slightly shorter acting agent that he can control more easily. We've been approved for a clinical trial, but it never got off the mark. And this was Epi-743 is the agent. And I would say it's because the issues that began aligned got misaligned. And I'll tell you what I mean by that. So this company that makes Epi-743, which I will call a version of idibanone, let's call it super idibanone if you wish, in the Petri dish has potential advantages over idibanone. So we were able to enroll 12 patients. And about a third of them, well, you're going to give the results, but more or less, a third did really quite well, a third did a little bit better than we would have had without treatment, and a third didn't respond at all. So positive, but not, it's no magic bullet. So then the FDA came back and said, perfectly appropriately, no more. 12's enough to get a good sense of it. It's not toxic. It might work. Let's do it properly. Double-blind, placebo-controlled trial. And that's perfectly reasonable. The company wasn't so happy because this sort of trial is actually very expensive, and after a lot of negotiating decided to pay for it, wrote the check, and meantime I had gotten the IRB at USC to approve, except at the very last second the IRB says, wait a minute, this new paper just came out with idibanone working pretty well. Certainly doing something positive and helping. And so the group in Newcastle with a prospective trial and Valeria and I with a retrospective trial have just demonstrated idibanone works. How can you ethically take 50% of the patients, randomly selected, I wouldn't know who it was, certainly the patient wouldn't, and put them on sugar when there's idibanone? So the IRB said you can't do that. The proper way to go is to compare idibanone to Epi-743, so everybody gets at least one or the other. Sounds like a great idea. Talk to the FDA. Wonderful idea. Talk to Edison. No way we're going to do that. We don't want to go head-to-head. Too much to lose. So this has led to a series of issues where somebody is always unhappy, and we as the investigators, and especially you as the patients, are sort of caught in between. So the check is not in the mail. It's sitting uncashed for about a year.
We're going to do a subset analysis retrospectively on those patient groups to see which is might be select for subset patients.
I'm sorry, a subset analysis for who's responding and who's not? We have done that using the 12 patients treated in the U.S., and to that we add 6 patients from Brazil and 3 from Italy. And I can just tell you one thing, and then I'm going to let him give the data. But the one thing is that which makes the most sense turned out not to be true. So, for example, the instinct we always had was get in there earlier. And, you know, in every disease you can think of, earlier treatment works better than later treatment. And one way we were able to sort of line everything up was not by comparing one patient to the other, because they just varied too much in terms of when they showed up for treatment, but comparing the same patient, one eye versus the other. So for every patient we had, the first eye went longer before treatment than the second eye, because you give the treatment by mouth. So the second eye, in its course, gets treated earlier. And the assumption was the second eyes would do better than the first. If it had turned out that way, there still could have been an argument, because typically the second eye does better than first in other diseases. Because if you have macular degeneration or glaucoma, the first eye you diagnosed in probably was worse in the first place. But it turned out to be the opposite. The second eye ended up doing worse than the first. So how could it be that getting in earlier with this treatment was a problem? I can speculate wild fantasies, but it's not clear.
Can you speculate, or did you say, and I didn't understand, the reason for the pattern from spatial implementation?
Yes. Yes, it's a surface area to volume ratio. It's the same reason that if I'm in an airplane and I dump out an elephant, that elephant will fall fast and hard and die. But if I dump out of that same airplane a cockroach, it'll survive the landing. And they roughly have the same shape, just one's much smaller than the other. But in the case of the elephant, the amount of surface area it has, if you take all the skin of the elephant and divide it by the weight of the elephant, that is a much smaller number than doing the same thing with the cockroach. So since the air resistance to surface area and the weight is fighting against that, you end up killing the elephant and saving the cockroach. In that same surface area to volume ratio situation, the smallest fibers are much more vulnerable because they can't produce as much volume of mitochondria for the surface area that is the expense of that fiber. They are in, I guess, a better analogy, I tried this one for the first time with the elephant, never used it before, but a better analogy is this one. If you go into a cold climate, the baby's going to freeze before the parent freezes, because the baby, by being smaller, has much more surface area, which is where it loses its temperature compared to the volume that generates it. And that's close to this analogy because the mitochondria in both cases is making the energy.
What is it that we're losing?
The smallest fibers.
I mean, why are they dying first? Is it ischemia?
No. They probably are going through this cascade where the reactive oxygen species comes to a threshold level that signals the mitochondria, the same signal that it's used for good purposes under other circumstances to commit self-suicide. Just to give you an idea about why the machinery is there, when you were about 4 months of age, you had 5 million retinal ganglion cells connecting to the brain. And then a wave of signal comes through that says, only the guys who are really well connected to survive. Let's prune this system so 4 million of them died by a wave of apoptosis. So it's a good way that the body can adjust things. And it uses the same signal then. But the last million, you don't want to lose.
So you're saying that they're putting out per unit volume more ROS than
Yes, that's exactly it.
And why is that?
Because they have more work to do on their surface with only a few mitochondria to do it with. Let's use real numbers. Maybe that'll help. Let's say that I got a fiber that's got a diameter of 2. The amount of surface area goes to the square of that number. So we're going to use just this random unit, 4. But the amount of volume, how many mitochondria you can do, goes to the cube, which is 8. So now you've got 8 supporting 4. But if I made the numbers 10, then the square of that is 100. The cube of that is 1,000. So now you got 1,000 versus 100. So you've got a much, much worse ratio now than you had the first time. So it doesn't scale. I guess that's the simplest way of saying it. And people don't realize how much that's an effect in biology. You just assume that because it works on a movie theater, that a little tiny dinosaur can be made to look like a big dinosaur, that it's all the same. It's not. It doesn't scale. No. And the reason is that most of the systems that you might be thinking about, there are a series of retinal prostheses, work in the opposite way. The retina is not working, so you stick in the prosthesis to do the work of the retina, and you plug in to the same optic nerve that is working. In our case, the optic nerve, the cable's cut. A prosthesis would be buying a new video camera. If the cable's cut, you're not going anywhere.
No way of bypassing the damage.
Sticking it straight into the brain. It's actually been tried. There's a Dubel implant system that was developed about 30 years ago in New York. The fact that you haven't heard of it is because it was a disaster. Okay. I've taken up too much time, Lisa. I feel very guilty about that.
Thank you so much, Dr. Sadun. We're a little off schedule, but I think you'd all agree that was worth it. I think we'll go to the next speaker and then take the break after he's spoken. There is a door there if you do need to, take a quick break. But I think we'll just keep going and we'll, bring things back together. Maybe shortening a break or running a little bit long into our networking time, but I just want us to keep going here. I wanted to just quickly mention, I had mentioned earlier how grateful I am to the UMDF, and I did want to point out that Chuck Moen, CEO, Chuck, great. Chuck is the person who just, when I said, hey, can we get LHON collaborating with UMDF? And he was like, absolutely, let's make this happen, go, go, go. And I just want y'all to know how important he's been to making today happen and huge support for what we're doing here. One of the exciting opportunities with LHON, as you've been hearing through the discussion with Dr. Sadun, is that it's an international situation. It's not local. And the patient community is learning to do that very well. As many of you know, we have a Facebook group with over 1,100 participants from around the world. In the Facebook group, we have people in Japan, Indonesia, India, Croatia, Germany, the UK, Italy, Canada, the US, many, many more. There's patient groups having meetings like this in France, Sweden, Spain. We think we're forward-thinking doing it here. They're doing it in other places. The LHON research community, as you have just seen, also crosses borders, such as at this event, where there are researchers from several countries with a specific focus on LHON. Who did I meet from the Netherlands yesterday, I think, is in the room. And one of the finest is our second speaker today. Let me read you his bio. Valerio Corelli has been a researcher in charge of the Laboratory of Neurogenetics Department of Biomedical Sciences and Neuromotor Pathologies at the University of Bologna, Faculty of Medicine and Surgery in Bologna, Italy. Dr. Corelli is currently a research assistant, professor of ophthalmology without remuneration at the Department of Ophthalmology of the Doheny Eye Institute, USC, School of Medicine, Los Angeles, California. Dr. Corelli earned a degree in medicine and surgery at the University of Bologna. He specialized in neurology at the Neurological Clinic of the University of Bologna and earned a PhD in neuroscience at the University of Verona. Please welcome Dr. Valerio Corelli.